let's see. So that's the course outline. This is the first lecture. We're going to go up until up until a certain point in the course, where near the last two, it might be 3 sessions, depending upon how many groups we have, they're going to be student presentations. So that's the way the course is going to go. And the first half is about linear models, and the second half is mostly about nonlinear models for correlated data. So that's what this list is. That's what this list describes. And again, the prerequisites for this course is fundamentals of epi, fundamentals of biostatistics, linear logistic and Poisson regression models, just like in Epi 740, and experience using computer package, just like in Epi 740 and other courses you've had. Okay, so that's my overview. Okay, so I'm done with that unless you have any questions. Okay, so let me get out of that. Let me get to what it's all about. What's correlated data about? Okay? That's what we're going to start doing. And I'm going to talk for about half an hour or 3/4 an hour, then we're going to take a break. Okay? So, what are correlated data? What are some of the key issues? Say something a little bit more about the procedures, what some examples, the data framework, and the types of models, and this whole business of why worry? Why do we want to have this course? Why are we having this course? Why is it there? What could go wrong? Okay, so to talk about correlated data now is, first of all, there's a whole bunch of synonyms that are used to say the same thing. Talk about correlated data analysis, you say correlated, you can talk about clustered data, you can talk about repeated measures data. These are 3 things that are all basically general terms for data in which the same observation is measured on several occasions on members of a given cluster. That's what we're talking about in very general terms about what we mean by, we're talking about something called a cluster. Now, a cluster could be an individual. The clusters in your study could be several individuals, could be 100 individuals, and each individual, you've measured something several times. You've measured their blood pressure 6 times, 10 times. So you have 100 individuals, and you've measured their blood pressure several times. The cluster is, you've got a cluster, a bunch of data on a given number of individuals. Okay, so that's a key thing. Key word there is cluster, but there were all sorts of terms for. Once you have this problem with cluster, the thing you're worried about, well, what are you worried about if you have a cluster? What do you think you're worried about? You have 6 observations on the same subject. If you were doing logistic regression, like we did in the Epi 740 course, and we had a data set, what we typically do when we're doing logistic regression, we say we have several different individuals. We know whether they got the event or they didn't, 0-1 outcome. And what we typically assume is that whether one person got the event or another person got the event, it doesn't depend upon each other. In other words, the outcome variable is independent on the individual. Okay? However, when we have clustered data, what you're worried about is that the repeated measures, or the measures within the same cluster, aren't independent of one another because they all have something in common. They're the same person. They're from the same family, something like that, right? So that's the problem. And then the problem is, if you're worried about that, if you're worried about the fact that you don't really have independent data, what do you have to do to account for that? And that's what the whole course is trying to do, trying to describe what do you do to account for the fact that you may not have independent, and how much of a difference could it make? Okay, so that's what in longitudinal data is a special case of correlated data where the clusters represent different subjects with repeated observations over time. So when we talk about longitudinal data, we're measuring something over time. Time is the way the repeats come, or the cluster or the correlations are brought into play. You could have correlated data that's not longitudinal, as I've got some examples. And as the first example says, observations on different members of the same household. So suppose you've got a study where you have 100 households. and you've got several people in each household, and you're measuring, blood pressure, or you're measuring whether they have a certain illness, whether they have the flu or not, or something like that. Well, what you might expect is those people that are within the same household, their outcomes are not independent of one another because they're within the same household, either because they're in the same family or they're getting the same exposures and stuff like that. So you can assume maybe, or you may worry about the fact that the data within a household, or the outcome data that you're looking at, isn't independent. They're not independent of one another. And so you can't necessarily do the usual type of thing, doing the usual kind of logistic regression, Poisson regression, or survival analysis that you might want to do because there's correlation involved. Even though you've collected the observations within the household maybe at one time, or roughly at one time. You went into the household and you asked people what their blood pressure was at roughly around the same time. So you haven't collected the data within a household, the cluster, over time. You've done it at one time. So time's not an issue here, but you do have correlated data to worry about. So you could have observations on different teeth on the same person. It's the same person. So they're correlated. Observations on each eye of the same person. Data on twins. Twin studies typically involve worrying about correlated data. Results of bypass surgery on different subjects, and I got an example of that where you got subjects where you take a given subject, they've got some blockage in their heart valves or in their arteries, and you're trying to unblock them, and you may have to do more than one bypass. There may be more than one artery or one vein or whatever that you have to put a stent in. And so you've got observations on the same subject in different places on the same subject. It's not over time, it's at one particular time that you're doing the surgery, okay? But they're correlated, okay? And then observations on rodents from the same litter, just to make the point that the data doesn't have to be on humans that we're talking about. It could be on animals. So a lot of people do correlated data analyses on studies that have to do with cattle or in the food industry that have to do with whatever the animals are that you're dealing with in the food industry. So, okay, now let's talk about notation here. Okay, now when you talk about cluster data, I've got some notation here I want to talk about. Now, the Y typically denotes the outcome variable. Y is the outcome variable, whether it's systolic blood pressure, whether it's whether or not somebody's sick, whether they have a certain illness or not, they have the flu or not, or whatever. So, and if you have a cluster, we're going to talk about the ith cluster. So if we have a whole bunch of subjects, 100 subjects, we're talking about any one of those subjects might be a cluster. And we're talking about the ith cluster, or it could be the ith household. Okay. Now, typically you might say the number of clusters should be denoted as, the usual term is n. N for the sample size in some sense, but that's not in the standard literature. So the total number of clusters is often denoted by, and that's what we're going to use here. Even though you could, as long as you're, you can handle it, you can use whatever you want, but I'm going to be using the notation K for the number of clusters. If we're talking about subjects, which have repeated measures on, there will be K subjects. And the ith one is the ith cluster within those K subjects. Now, if we're talking about repeated measures within a given cluster or within observations within a household, then the number of observations within the ith cluster is going to be denoted as n sub I. N sub I is the number of observations within the ith cluster. So we got I, the cluster, we have n sub I, the number of observations within the ith cluster, and we got K, the total number of clusters. Okay. Now, you can imagine that this is starting to get a little complicated because when you start and then I haven't even talked about the X's yet. Those are the predictor variables. But just in terms of the y's, things are getting a little complicated. Now, one thing you notice, now, at the bottom of the screen here, I've got a picture of two situations of longitudinal data related to, we're assuming that the cluster is a subject, and we've got two different subjects here. And what do you notice about this picture? What do you notice is, first of all, the subject at the bottom, or the graph at the bottom, has 4 x's. So there's 4 measurements being done for that, in that cluster. And the one above it has 5 measurements. Okay? So what's n sub I here? N sub I is 4. N sub I here is 5. Right? So what that tells you is that in general, when you're talking about correlated data, the number of observations within a cluster might not be the same. Right? You could have 4, 5, 10, it could vary all over the place. Okay? And that's sort of a worry, because if they're different, then you have to worry about, well, how much different are they, and what do you do about the fact that they could be different? There's something else in this picture, though, that not only are the number of observations different between these two different clusters, what else do you notice? The times at which they're observed are different. So you can have a different number of observations than they were observed at different times. And if that happens, you have another complication. Okay? Now, if you have this general complication that I'm sort of showing you here, you can still do a correlated analysis. There are, what we're going to describe how to do it, and the models that you could use, and the ways you could even set up the data, still work for that more general situation. But if you try to work them or deal with that situation, it turns out that the analysis gets a little hazy, or there's more things you have to worry about, or more assumptions you have to make to try to get it to work. So even though you can do something with it, what you often wind up is having to make some assumptions, or you have to make some simplistic ways of thinking about the data in order to get the analysis to work. So ideally, what you'd like to have is for every cluster, or every person, or every household, have the same number of observations within the same cluster. That's what you'd like to have. Everybody have 5 observations, 5 measures of blood pressure on each subject that you have in the study. Now that typically doesn't happen. Although you can design a study to hopefully make that happen, even though it may turn out that you don't get what you always want, and then you're stuck in this more general situation. If it turns out the number of observations within a cluster is the same, things work out a lot better. So when you start thinking about your project and what your data set is for your project, if your project is more general, like what I'm showing you down here at the bottom, you're going to have more things to kind of deal with, which is maybe a good thing to have to deal with it, because you're going to learn about, how to deal with it. But it might be a good idea to, if you even have that situation, just to take your data set and try to consider it in a way that, to take a subset of it, where everybody has the same number of observations, and try to do the analysis that way, and then show how it compares to what you did when you had unequal numbers. So that's a way you could, you could work that into your project and see how things differ. But of course, we need to talk about how to do this thing. We haven't done that yet. But anyhow, that's the key issue here. So now, by the way, I've written Y in bold, this Y, and I've written these Y's, they're not in bold. Okay, so the Y in bold, the bold represents a collection of outcomes, or collection of the outcome variable. Okay, collection of values of the outcome variable, and this is the collection. So the bold really refers to the cluster, and the unbolded ones refer to the observations on different people within a cluster. So that's going to be a general way to distinguish the cluster from the individuals within a cluster. Now, some of the further notation we're going to get into a little bit more when we start talking about matrices, so I'm not going to get into that. The tilde underneath, the tilde, that's a tilde, for those of you who speak Spanish fluently. No, I don't know. anyhow, or the twiddle underneath this thing. That's just to denote that it's sometimes when people try to type it on a computer, the bold doesn't come out. So the tilde is trying to emphasize the fact that it's meant to be bold. So it doesn't need to be in there as long as you can see the bold, but I've left it in. I probably should have taken it off, but I've kept it like this. Okay, so anyhow, methods for analyzing correlated data. Let's talk about that. Now, I'm looking at the clock here because we're getting close, but we're not there yet in terms of a break. There are two general ways for analyzing correlated data if you're talking about modeling approaches. One is called Generalized Estimating Equations Approach, or GEE, Generalized GEE, gee whiz approaches, okay? And the other are maximum likelihood, ML, or REML, R-E-M-L based approaches. Now, REML stands for, the RE stands for restricted maximum likelihood. So the ML is still maximum likelihood. There's a slight difference. We'll talk about that when we get to it. Okay. Now, it turns out that so there are two different types of approaches, and you've learned about maximum likelihood last semester, or you even may have learned it before. Maximum likelihood is when you have a data set, you have a model, you come up with a likelihood function, and then you use some computer program that maximizes the likelihood function. And you may remember that when you maximize the likelihood function, you want to test hypotheses. There were two kinds of tests. What were they called? Likelihood ratio test and wall test. So I'm doing a very fast review of what you should already have sort of under your belt in some sense. Okay, and so there's maximum likelihood. It turns out that the mixed procedure is essentially a maximum likelihood approach. The NL mixed procedure, what's, as I say here, rarely used and not strongly recommended, is also a maximum likelihood approach, but we're not going to get into it because it's not as good as some of these other ones. And then it turns out that GLIMMIX has got an approach that's a GEE version and a maximum likelihood version of GLIMMIX. And the maximum likelihood version is very new, and as I said, it may be a replacement SAS for NL-mix, and I'm not really comfortable or familiar with this part of GLIMMIX. So the GLIMMIX that we're going to talk about is in the term of generalized estimating equations approach. Now, when you're talking about generalized estimating equations, the GEE approach, what you're talking about is you're not dealing with a likelihood function. You're dealing with some problem of correlated data that you want to come up with an analysis to try to come up with estimated coefficients and maybe get odds ratios or estimated regression coefficients. But you're not going to assume that you are able to come up with a likelihood function because you don't actually know the distribution of the outcome. You know, if you're dealing with normal data, normally distributed data, you can talk about the normal distribution, and you can come up with a distribution, that a formula that allows you to write down what the likelihood function, and then the computer can maximize it. But when you're dealing with more complicated, particularly nonlinear data, it's not very easy to write down a likelihood function. And so these generalized estimating equations approaches are ways to come up with an analysis that don't involve maximizing a likelihood function, but involve solving a set of equations. You remember when you're doing maximum likelihood, what you wound up doing, even though the computer did it for you, it solved a set of equations and gave you what are called maximum likelihood solutions. Well, when you're doing GEE, you're also solving a set of equations, but they're not maximum likelihood equations. They're based on some other way of thinking about where the data is coming from, without assuming that you know the distribution of the data. So again, we'll get into that. But so there's two alternatives. Okay, and there's a lot of different software that one could use, and I'm going to focus on item number one, and that's what you're going to mostly focus on. Probably a good idea for this course, because there's so many other things to learn about how to do correlated data that if you start doing other packages, unless you're very familiar with other packages and you want to use other packages. How many are more familiar with R than they are with SAS? Is that true? Nishan. So you may want to do your project in R. Well, you're not sure, but you might, and that's fine. Okay. Anybody else more familiar with Stata? You know, Stata is a package that's used very frequently in Europe and in other parts of the world. Now, why do people like R? Why do people want to consider using R? Because it's free, right? Did I say that? Yeah, I said that. Okay. So now let me say a little bit more before we take our break here. Okay. Let's talk about GEE, the statistical theory for GEE. And again, it's more general. It's different from maximum likelihood. In fact, it's different because it's based on some theory which is called quasi-likelihood as opposed to maximum likelihood. And we're going to talk about what quasi-likelihood is later down the road when we finish dealing with linear models, when we don't have to worry about generalized estimating equations. But quasi-likelihood is an extension of maximum likelihood. It's a more general way to think about likelihood. It's an extension of it. And also it turns out that GEEs is an extension of something, of the theory of what's called generalized linear models, which combine continuous and discrete models into one common framework. Now you've already, again, when you were dealing with the Poisson regression model last semester, have already dealt with a program called GenMod, which is set up to deal with a whole bunch of different kinds of models. In fact, GenMod, what you learned to some extent last semester, in order to describe the different kind of models, you have to tell the program GenMod, you have to tell the program what the link function is. If you're doing Poisson regression, what's the link function? Do you remember? I already mentioned it earlier today. Link function is the log link. It's a log link. Okay. If you're doing logistic regression, GenMod could be used to do logistic regression, even though there's a program called ProcLogistic that you spend most of the class learning how to use. GenMod could do logistic regression using what link? A logit link, not a log link. So GenMod is a package or a procedure that allows you to use a lot of different models. And it's a generalized way to consider a bunch of models. And in fact, it doesn't have to be, it's called generalized linear models. Now I'm going to be talking more about this later, but I don't know if you remember this, but when you're dealing with logistic regression model, you remember the logit function? Remember what the logit function was? It was the log of the probability over 1 minus the probability, the logit function. You remember that? Hopefully, you know. Do you remember that if you had a logistic model and you took the logit function, what does the model turn out to be? The logistic model is 1 over 1 plus e to the minus something. It's a nonlinear model. But what happens when you take the logit function? You get a linear model. You remember that? So you can go from a nonlinear model to a linear model by taking the logit function. And so that's why the logistic model is considered to be an example of what's called a generalized linear model, because there's some part of that model has got a linear component that you can get out. Same thing true for Poisson regression. If you take the log of a rate is usually linear. So when you're doing Poisson regression, there's a linear component of it. So that's what you mean by generalized, and we're going to get into that, but that's maybe as important as anything just to say this here. Okay. Now we got to talk about correlation structures. This is the key issue that I have to say before we take a break here. I have to talk about correlation structures, because that's what we're really worried about. You know, we're worried about the fact that, well, we maybe don't have independent data. Okay. So the data is correlated in some way. In what way is it correlated? And how are we going to figure that out? Okay. Well, it turns out that, first of all, as I say at the top of the screen here, correlations are primarily considered a nuisance. A nuisance. What do I mean by that? Because they're almost like a covariant. You're not really interested in the correlations other than the fact that you want to account for them. You know, when you're dealing with a confounder, you want to account for it. But you're not really interested in the effect of the confounder. You're interested in the effect of the exposure variable. So it's not the primary question of interest. That's the same thing about the correlations. You want to account for it, But it's not, you want to do a good job of accounting for it, but that's your main goal is there a relationship between exposure and disease, given that I have correlated data? That's what you want to do, okay? So that's one thing you have to think about, that you may want to be able to do a reasonable job of dealing with this nuisance that doesn't get exactly what those correlations are. That's a way of thinking about it. That your goal may not be to exactly pin down what those correlations are, the correlation structure, but maybe to account for it in some reasonable way. And now what typically you wind up having to do when you're doing correlated data analysis, you have a program like GenMod or a program like Mixed. And when you're using the program, you have to tell the program what you think the correlation structure is. You have to guess at the correlation structure. Okay? One correlation structure to guess at is that everything's independent. Well, that's what you were worried about in the first place, but that's one way. Another correlation structure is that every correlation of every observation of the several observations on the same people, every pair of observations, correlation's different. The correlation is different. That's called a unstructured correlation matrix. All the correlations are different. There's another one. I'm just talking about it. There's another one, but I'll actually show you. Another one. Look at this one over here. See exchangeable? What does this say? All the correlation allows for, in this case, you're talking about a person who has how many measurements? This is what kind of a matrix is this? It's a matrix. It's a 5 by 5 matrix. Now, on the diagonal of the matrix, you see the number 1. What is that? The correlation of any observation with itself, right? What's this? This one. Rho. It's the correlation of the first observation with the second observation, right? And this one is the correlation of the first observation with the fifth observation. This assumption, or this matrix, it's a structure. This assumption, or this structure, assumes that all the correlations are the same, regardless of whether you're talking about the first and second, the first and the third, the second and the fourth, whatever it is. That's another term for this is exchangeable. Okay? So that's a choice. There's unstructured, there's independent, there's exchangeable. Oh, there's a million of choices. Now here's another one that people like, called autoregressive. Now, is autoregressive unstructured? Unstructured means that all the correlations are different. Are all these correlations different? You see there's a rho square in there a couple of places, right? Okay, and there's rho in there a couple of places. Okay, so they're not all different. They're not all different. This is actually saying, now if you think about this, you look at you see the row here and the row here and the row here? This is the correlation between the first and the second observation. This is between what? Second and the third, right? What's this between? Third and the fourth, and between the fourth and the fifth. So what you're assuming in this thing is that the correlation of any pair of observations that are 1 unit apart, first and second, second and third, third and fourth, are the same. See that? What about if they're 2 units apart? What's the correlation? Rho square, right? Regardless of whether it's 1 and 3, 2 and 4, right? And what if they're 3 units apart? It's rho cubed, right? So what's happening here? Well, it's not unstructured, so what's going on? Now, just for, it doesn't have to be, but let's assume that rho, the correlation, is a positive correlation. So what happens when you go from rho to rho squared to rho cubed to rho to the fourth? What happens? It goes down. Correlations go down. Why might that make sense? Because as observations get further and further apart from one another over time, if you've got a study over time, you may not have a study over time, so you may not be able to say this, but if over time they're further and further apart, you might think they're less correlated. So this autoregressive structure is one that a lot of people like. They like this often better than this one in a situation where you're dealing with time. Okay? Now, it could be you're dealing with time, and the time between observations, the study's not that long. So it may turn out that as you go from one time to the next, it's not that long a study, so maybe the correlations don't change that much. So you might still consider exchange. But this is a problem that you have when you're dealing with the correlation structure. There's a lot of choices. And this is not the only choice when you did the one at the bottom here. It's not the only choice when you're dealing with correlation structures over time, when you're worried about time. There are other choices. There's another one called stationary that I'll talk about later that a lot of people like better than autoregressive. Doesn't make as much assumptions, but we'll get to that. But look at what I say here. The GE approach requires the user to guess the correlation structure appropriate for the data. Guessing the structure. Okay? You have to tell the program what you think the structure is. Well, however, now I say something at the bottom, however, the results obtained are often robust to the choice of correlation structure, though the choice of correlation structure still remains an issue. So what does that mean? What does that statement mean? This is just English, but it's gobbledygook English. I don't know. What does that mean? Okay. What it says is, okay, you have to guess the correlation structure. But what it sort of says is that even if you don't get it exactly right, it may turn out that you get the same answer no matter what you choose. Isn't that what it says? It's robust. Doesn't really matter if you don't get it exactly right. Okay. Now, that's nice to know, but it turns out it might matter. It's the problem. So the word is often robust, okay, but it may not be, it may not work. So what do you do? I mean, this is a big problem when you're dealing with correlated data. In practice, what do you do? Well, you guess this, you guess that, you guess that. You look at your answers, you maybe look at whether they're the same or not. Well, it turns out there's a way when you're running these programs to adjust the answer that you get for the fact that it may be wrong, that the correlation structure may be wrong. In other words, you choose exchangeable. You tell the computer, I'm going to run exchangeable. And then you run it, but then you also say something in the program, I want you to adjust for the fact that maybe I made the wrong choice. It does some kind of adjustment process. So this is something you could do when you're running correlated data. And this is a nice thing that people like. Okay, so you can get an adjustment. The problem, and this is where this thing is a little bit weird, is the problem is if you choose exchangeable and you adjust for it, and you choose autoregressive and you adjust for it, and you choose unstructured and you adjust for it, well, you often get almost the same answer, but you may not. And if you don't get the same answer, what do? So that's still a problem. So one of the biggest things for this course is how do you choose this correlation structure? Now, it turns out that, now this is where I got to get ready to stop here. It turns out that within the last year, SAS has come up with a procedure. It's got a name. It's called the Cove test procedure, C-O-V-T-E-S-T, called the Cove test procedure. And it's a way that allows you to do a little bit of a better job of checking whether you got the right correlation structure or not. Or it allows you to do a test of whether two correlation structures are different. Up to this point, you just had to guess and then you had to adjust for it. But now there's a way you can do a statistical test for it. But unfortunately, fortunately, there's this test there now. But the test was only put in glim mix. Wasn't put in mixed. Okay, it was only put in glim mix. So if you're using glim mix, you can use this test, okay, this Cove test. Okay. If you're using GenMod, it's not in there. If you're using mixed, it's not in there. But there is a way out as far as glim mix is concerned, because as it turns out, glim mix is a generalization of mixed. So it turns out that glim mix includes mix as a special case. So if you've got a linear outcome, if you've got a continuous outcome, you could use glim mix to do it. I don't know if you get what I just said. You can actually use glim mix to fit, you don't have to use mix to fit a linear model. You can actually use glim mix. And then you could use this Cove test option. So this is something that just came out recently. And you're going to learn how to use that. I mean, we put that into the course last year, and it was new. Okay. So So let's see. It is about the time to quit. In fact, it is time to take a break. It's 10 to 4. Could we come back at 5 after 4? Will that work? Can you handle that? 5 after 4? So I'm giving you about 15 minutes as opposed to 3 minutes? 15 minutes? So it's a little less than 15 minutes. So at 5 after 4, I'm going to start talking again about this. Okay? How many of you more or less followed what I've just done? You more or less followed? I mean, I didn't get into the heavy-duty math thing, but and I'm just talking about it generally. But this is the basic stuff. Okay? See you at 5 after 4. So let me go to this.
I'm failing. I have a 4 o'clock.
Hey, yeah. You fine? Follow that?
Yeah. I've done conference.
Done
You
it.
know, that's how you do that. Controlled crossover beam studies. Is
Oh, yeah,
realizing
okay.
across-
You've done repeated and random stuff.
Yes, yeah.
Yeah.
But it hasn't done. I'm not lost yet.
Okay, no, good. Well, I hope not. I didn't do much. Let's see. Okay. How are we doing? Questions? Everything perfectly clear? Who said totally? That's what I thought. No. Okay, so we've talked about what correlated data is about, what the notation is. We've talked about the computer programs. We've talked about the different methods of estimation, GEE versus maximum likelihood. We've talked about correlation structure. And we've talked about quasi-likelihood a little bit and what generalized linear models were. Now what I want to do is given all of that, I have a slide here which says goals of longitudinal research. Okay. Now, more generally, it probably should be saying, and I haven't changed it, goals of research involving correlated data. So there are 3 things listed here. The first one says to characterize patterns of subject responses over time. Okay. Now that statement really relates to longitudinal data because if we're talking about correlated data in general, you might have data on households. So it may be you don't have time even as a factor in there. So time might not be a factor. So the first item more or less refers to longitudinal research to see what's happening over time, comparing, whether how things for one person or one group of people are changing over time compared to another group of people. The second statement says to investigate the effects of important covariates or predictors on these patterns. Now that statement is a more general statement. It doesn't depend upon whether it's longitudinal or correlated data. You basically want to do what you typically want to do in any research study where you have covariates, and actually the fact that I use the word pattern still makes sense that you're still dealing with time. But if you're talking about some model to describe the relationship between an exposure and an outcome, and you're controlling for some other variables, then you're talking about a more general situation that's not generally related to time, more general correlated data situation. And then the third statement says, to predict y as a function of some set of predictors. That's sort of a more general way to state a way of saying what your goal might be as far as correlated data research, even over and above longitudinal research. But the only problem with statement 3 one might take issue with, and I've just listed these 3, I'm just talking about them a little bit. But the only problem with statement 3 is you may not have the goal of prediction. Your goal may not be simply to predict y. It may be more related to etiology, more related to trying to describe a relationship between one or more exposures and an outcome, which might not, the way you might go about doing that is not using a model that's the best predictive model. So the third statement it might ought to be a fourth statement, which should be saying to describe the relationship between one or more exposures and an outcome controlling for covariates in the context of correlated data. That should have been on this list, but I didn't remember that I had missed that one there, so I only have 3 of them there. But now let's get this, and let's talk about some examples. Examples. These are examples I'm going to talk about in general, but I don't have data. Well, I do have some data on some of them that we'll talk about later. But suppose we're talking about a cancer trial, cancer patients, okay, and the patients are being followed over time, and you're measuring monthly measurements of quality of life. You're measuring treatment status and therapy type. In other words, a patient may be getting a certain treatment, but they may be getting it in different ways. They might be getting it very intensive or not so intensive, or regular, more shots of something or more chemo per day than another kind of therapy. So, but the question that I'm asking here is, if this was the cancer trial, and the question was, how does quality of life relate to treatment, therapy type, and possibly other predictors of interest? Okay, so what's the outcome variable here, based on what I'm saying? What's the outcome? Quality of life. So in a way, we've got cancer patients, you might be following them to see how long they live and and that might be a survival analysis problem. But in this case, we're talking about patients that you're measuring something several times, several months, and it changes quality of life. So you want to know what predicts their quality of life. And you've got several variables: treatment, therapy type, possibly other predictors of interest. So is this a correlated data study? Is it a correlated data study? Or is it a longitudinal correlated data study? You would think yes, because you're measuring something on individuals, on the clusters of what? The patients, and you're measuring their quality of life several times over the course of their treatment. Okay, so so quality of life, that's the outcome variable. What kind of variable is that? What kind of a variable is that? Well, it depends, right? I mean, it could be you have a scale, some kind, and you measure quality of life according to the scale, and you measure a continuous thing. So if it was quality of life was measured as a continuous variable, what model would you think you ought to try to fit to this data? It's a continuous variable. A linear model, right? That's the kind you might think about doing. And if you were fitting a linear model, what program of the ones I've mentioned might be more relevant to dealing with it? Well, of the programs, what's the one that's really specific to linear models? Even though the other ones will let you do it, it's mixed. So if it's a continuous outcome, the first thing you think about is mixed, even though you could use some other programs to do it. You can actually use GenMod and GlimMix to deal with continuous ones, but if it's continuous, mixed has been around for a while, and that was set up to deal with a continuous outcome. Okay, now, I'm just trying to go over the example. Is it definitely a correlated data problem? I mean, is this correlated data? Do you have to account for the fact that there's monthly measurements over time? Do you have to account for it? Do you know for sure that if you don't account for it and assume that everything's independent, you're going to get a different answer than if you do a correlated data analysis? Do you know that? Well, you never know. You really never know. So what it may turn out to be that, and you have a situation where you know that you've measured something over time and there's potential for correlation problem that you have to account for. That's the kind of situation you certainly going to want to consider doing a correlation analysis. But it doesn't mean that you would get a different answer than if you assumed everything was independent. Okay? So you can always do that. You can always do them both and see whether it makes a difference, which is something, again, related to your project. When you decide on a project, it may turn out that for your project, even though it might make sense to worry about whether there's a correlation thing to worry about, correlation structure that you have to worry about, it may turn out that when you account for it, it doesn't make any difference. Okay. Now, okay, so what correlation structure? That's another question. So it's all with this one example. What correlation structure would you consider? Autoregressive, exchangeable, unstructured. If you wanted to allow for non-independence, I'm saying. Exchangeable or autoregressive, if you had to choose between those two. Why? Because again, it's over time, so the advantage of autoregressive is that you're allowing yourself to account for the fact that as observations get further and further apart, their correlation gets smaller. That's why the first guess in this kind of a situation would often be autoregressive or something like that. I've mentioned something called stationary, but I haven't explicitly defined it or given you that. As opposed to exchangeable, because exchangeable is saying it doesn't matter how far apart observations are, it's the same correlation. Now that could be okay, and you could wind up getting the same answer. Okay, but in any case, so that's the first example. Let's look at the second example. 7-day diaries are taken recording child's illness status, yes or no, 0 or 1, and mother's stress levels. Also, race, marital status, employment status, and general stress level are measured. And the question is, how is child's morbidity related to mother's stress level and other covariates? So what's the outcome variable based on this, the way the question is worded? Child's morbidity status. It's a 0-1 variable. Okay. Are we dealing with correlated data? Or possibly? Because why? What do we have? We have this 0-1 variable measured several times, 7 times. 7-day diaries. Okay, right? So on a given child, we might expect whether the child is 1 or a 0 might relate it to whether on another day it was 1 or 0. So it looks like you might have to worry about correlated data. Okay. What about the variables involved in this study? What's the main variable of interest according to what was stated here? Mother's stress level. Mother's stress level. Okay. What kind of a variable is that? Remember when we talked about survival analysis, we talked about different kinds of variables? We talked about time-independent and time-dependent variables? What kind of a variable is that? If we're talking about a 7-day diary and you're measuring mother's stress level at each one of those days, that's a time-dependent variable, right? So it could be that that's your main variable of interest, a time-dependent independent predictor, okay, as opposed to a time-independent variable. Now, on the list under number 2, on the list here, there is some variables that are time-independent. Of course, one is race, one is marital status, assuming the study is short, employment status, assuming maybe it's short, but it might not be, and general stress level. That variable is certainly a fixed variable. It's not time-dependent. It doesn't change over time. General stress level. Okay. So here you can have a correlated, the message here is you can have a correlated data study where some of the predictors are time independent And some of the predictors are time dependent. That's the message here. Okay. And since the outcome is 0, 1, and you start thinking about model, what model would you think about using? Logistic and not a linear one. Okay. So if you're using logistic and not a linear one, can you use proc mixed? Can you use proc mixed? Proc mixed is a program which assumes the outcome's continuous. So you can't use proc mixed to deal with a logistic model. You can only use either GenMod or GlimMix to do that of the SAS procedures that are available. Just trying to give you an idea. What about the correlation structure? What about the correlation structure? So I'm trying to just go through these examples and get you to think about, and this is sort of what the first homework assignment is getting you to think about a situation, some kind of research situation, and then ask these kind of questions. What would be the correlation structure? What would be the model? What are the variables involved? What kind of variables are they? And so on. So what about the correlation structure? Let's put it this way. Exchangeable versus autoregressive. Come on, guys. Exchangeable versus autoregressive. Well, again, it's a 7-day thing, so it's changing over time. It's time is an issue. So you might say it ought to be autoregressive compared to exchangeable, but at the same time, it's only 7 days. So maybe things aren't changing. The correlation isn't changing much over time, so it's debatable. And of course, what you can do, as I've said, you could run a model with, you can tell the computer to fit exchangeable, you can tell the computer to fit autoregressive, and you can tell each time you can tell the computer to get a robust variance estimator, or adjust for the fact that you may have chosen the wrong one, and then you can look and see what kind of results you got. If they're the same, who cares? You don't really care. I mean, your goal is to deal with the correlation to get the right estimate of the effect, okay? Not so much to get exactly the right correlation. So if it doesn't matter and you get the same conclusion, who cares? Okay, now, you might care depending on what kind of a situation, but this one you don't care. Okay, here's a third example. Heart bypass surgery, not longitudinal. So you have a person who has 3 bypasses done, or 6 bypasses. Patients are given a variable number of artery bypasses in a single operation and randomly assigned to aspirin or placebo therapy. I actually have a data set with this. And 1 year later, angiograms are performed to check each bypass, which is classified as blocked or unblocked, 0, 1. What is the effect, the question is, what is the effect of aspirin on the risk of reocclusion, controlling for age, obesity, etc.? Okay. So, correlated data? Is it correlated data? Yeah, because on each patient, you could have more than one bypass. And those bypasses on a given patient, you would assume might be correlated because it's on the same patient. Okay. Now, it may not be, but that's, again, that's something you can always check. That's why it makes sense to consider correlated data for this situation. Okay, what kind of a model? Model. Logistic, right? Your first choice, right? Okay. Let's see. What about the correlation structure? What about the correlation structure? Exchangeable or autoregressive? It wouldn't make sense to consider autoregressive because you're doing these angiograms essentially at the same time, even though it's in one surgical procedure. You go from one to the next, but it's essentially at the same time. So it doesn't make sense to consider autoregressive or stationary because that's not changing over time. Now, there could be a different kind of correlation structure that may be something you could dream up or you can find in the computer program. The computer programs give you a choice of different things. There could be a correlation structure that involves how far apart bypasses are within the body. That's different than over time, but the distance of one bypass from another. So maybe that's something you could put in as a correlation structure, you know, in terms of another way to do it. But that's what I'm saying. There's a lot of different ways to do this. Anything else I want to say about this example? So what is the effect of aspirin on the risk of reocclusion, controlling for age, obesity? age and obesity are going to be treated as what kind of variables? Time independent or time dependent? Obesity probably time independent, and same for age. Although, age changes. Now you have to decide whether the time of the study or the length of the study, the age is changing, and you want to consider the fact that age is changing as a time-dependent variable. So you have to decide. But most of the time, you consider age at the start of the study. It's not that long a study. Obesity at the start of the study, and you're not really looking to see weight change or obesity changes, and you just want to. And the main goal is the effect of aspirin. So if you fit this model, let me just ask you this question: if you fit this model using logistic regression, and you ran a program, now it's not going to be mixed, as we said. It's got to be GenMod or Glim mix. Can't be mixed because it's not a continuous outcome. But you ran the program and you fit this logistic model, taking into account the fact that the data might be correlated. And let's assume it's a model that doesn't have any product terms. What's your exposure variable for this model? Aspirin status, right? What kind of a variable is it? 0, 1. What would be the formula for the odds ratio for the effect of aspirin status in this situation? No interaction in the model. What would it be? E to the beta, right? You learned that last semester. But what about the e to the beta in this situation versus what you might have had last semester when you were assuming everything was independent? What's the difference? Well, there could be a difference because now you're adjusting for correlation. So the e to the beta, you're going to compute it exactly the same way. You're going to use a program that's different from proc logistic. You're going to consider something with a correlation structure, and you can compute e to the beta, but it's not necessarily going to be e to the beta that you would get if you assumed everything's independent, because you're allowing for dependence or correlation. Okay? Okay? Is this easy? Yeah, I'm not getting into anything heavy here. Not yet. Okay, this is not the last one. Asthma study. Records of number of attacks per week, average weekly pollution levels, general fitness level, seriousness of disease. Question is, what is the effect of pollution levels on the number of asthma attacks per week, controlling for covariance? So what's the outcome variable? Number of asthma attacks that's measured 1 week, the next week, the week after, and so on. Okay. What kind of a variable is that? It's count, right? What model? Poisson, right? Correlated data? Probably, because you got several measurements on a person over time. So you would probably use GenMod or Glim mix. You couldn't use mix because the outcome is a count. And you would have to consider GenMod or Glim mix to do it, and your main exposure variable is the effect of pollution levels, so it's some measure of pollution, that's your exposure variable, on the outcome, which is number of asthma attacks, and you're going to have other variables you're going to control for. What about the correlation structure? Exchangeable, unstructured, or autoregressive, or what? Well, again, this is over time. So it might make more sense to consider autoregressive or something like that because you're allowing for the correlations to get smaller over time. Okay, now, here's a more complicated example. I'm looking at the clock here. More complicated example. Heart bypass surgery study number 2. Okay, we do this for a reason. It's a method to my madness, a madness to my method. This is a combined cross-sectional and longitudinal study. As in the previously described study, patients are given artery bypasses in a single operation and randomly assigned to aspirin or placebo therapy. Beginning of the study. At both 6 months and 1 year later, angiograms are performed and each bypass is classified as blocked or unblocked. What is the effect of aspirin on the risk of reocclusion, controlling for age, obesity, etc., correlation structure? Same question as before. What's the difference now? What's happening? What happened that's changed? Well, there's two different times when you're looking at whether these bypasses, whether these arteries were blocked or unblocked. You're looking at them at 6 months and then at 1 year, right? So what's the correlation structure? Well, when you start thinking about what's the cluster on a given person? So let's say a person has 3 bypasses. Okay, so the cluster is blocked or unblocked on what? How many measurements? 3 at 6 months and 3 at 1 year. So the so-called the outcome variable, the y variable, has 6 items in it. It has a 3 at 6 months and the 3 at 1 year. So what correlation structure is that? It's not that easy, because what's going on? At 1 year or at 6 months, either one of those times, we're talking about cross-sectional information. We're talking about not over time, within a specific amount of time. When we talk about 6 months versus 1 year, we're talking about a longitudinal part of the study. So there's a longitudinal part and there's a cross-sectional part. So the correlation structure is not obvious in terms of what it is. It's not obviously, well, maybe exchangeable would work if there's no difference 1 year, 6 months or 1 year. But to say it's autoregressive doesn't make sense, because there's a longitudinal component of it. So I'm just trying to show you that it gets complicated. There are situations where it gets complicated when you've got some combined situation like this, is to determine what the correlation structure. You can always guess the correlation. You could choose unstructured and then see what happens. See if it makes sense. And then look and see what you get and see if you see something better. Okay. There's even something we'll talk about later where you can actually, believe it or not, specify a numerical correlation structure. Rather than just say autoregressive or unstructured, you can specify numerical quantities for each of the correlations in your correlation structure. So let's say you had a person who had 3 bypasses. So that person has 6 observations at time, 3 at time 6 months and 3 at time 1 year. Okay, so their correlation structure, their correlation matrix is 6 by 6, because it's got 6 observations, 6 correlation times. One thing you could do is specify a numerical value for each of those correlations that reflect what you might think is cross-sectional and longitudinal differences somehow. Now, how you're going to do that is not always that clear, but you could do that, and then you can even run the model and ask for a robust estimator that helps to correct for the fact that maybe it's the wrong one. So there are things you can do even when it's not clear what to do. Okay, I'm just trying to get you to think about stuff like that. Rishon.
Could you treat the 2 measurement points as different clusters themselves?
Well, it doesn't seem like it's appropriate, because it's really, that person is the cluster. And so but there are some other things. There's a in the program Proc Mixed, but although this is longitudinal, even in Glim Mixed, there are choices of correlation structures you could use. And there is a choice in there that I'm going to mention when we start doing mixed later on. There is a choice that allows you to combine different things. That in the history of this course, I've described it every time, but nobody's ever used it. But it's a way you can actually take things that are either longitudinal or cross-sectional and put each one as a separate component into a correlation structure. And so that's, we'll talk about that pretty briefly. But I'm just trying to make the point that it can get more complicated. Okay, now, last example. This is something I've been spending the last several years. I work for DHQP, the Division of Health Quality Promotion at CDC, 1 day a week. My day is Wednesday, it's tomorrow. And they're worried about people who are resistant to infection in hospital circumstances. So here was, and I was involved in a study, an intervention to reduce MRSA occurrence carried out in a certain hospital. Okay. Now, it was an intervention study. So what happened was monthly MRSA rates were MRSA rates, in other words, a rate, the number of MRSA events divided by the, I think it's the patient time in the hospital, length of stay in the hospital for all the patients in a given month. Number of MRSA events divided by the length of stay of all the people in a given month were obtained for 88 months in each of 3 wards of the hospital. We might even think of it right now as just one ward. The same intervention was applied, but at different times, 25, 49, and 71 months in each ward. Now think of it, just not even worry about the 3 wards. Let's just talk about 1 ward. Now, what happened? What do you think happened? What am I describing? Well, what happened was, in this hospital, let's just talk about the 25. What happened was, they had these MRSA rates starting at month 1, going up to month 25, and then at month 25, they started this intervention to try to reduce the rate, okay? So they had a rates that were based on the intervention, no intervention, up until 25, and then after 25, there was an intervention to see whether the rate changed or not. Okay, that's the question. So, so what's the outcome variable? What's the outcome variable? Rate, MRSA rate. What kind of a variable is that? It's a rate. So what do you think should be done? Poisson regression. You might think is the first thing you think about. Okay, because it's a rate. Okay. Okay, now let's just think about the 1 ward, not the other 2 wards, because it gets more complicated. Okay. Now, what's the main question of interest? What's the main question of interest? You're looking at the rates up to, what is it, month 25, and then you're looking at the rates after month 25, right? So you got this variable that represents a treatment or intervention, okay? Up until month 25, the variable was no intervention. After month 25, there was an intervention, right? So if you wanted to define that variable, one way to do it is to say it's 0 up until week 25, and then changes to 1 afterwards. That's when the intervention starts. And that's the main variable of interest. You want to see if that variable shows some kind of a change in what happens when you look at the MRSA rates or the curve of the rates, or the plot of the rates. Okay, what kind of a variable is that? 0 until 25 changes to 1. Time independent variable or time dependent variable? It's a time dependent variable. Okay, so this is a study. So the question is, was the intervention successful in reducing the rates of MRSA occurrence? The outcome is rates. The main exposure variable is this variable. That's the intervention status variable. That's time independent. And what you want to do is have some model that allows you to see what happens before 25 months and then after 25 months. And that model is a little bit more complicated than just a typical linear model. It's not even a linear model, it's a Poisson regression model. It's a little more complicated, and it's called an interrupted time series model. It's like a segmented model. It's like a, there's another word. Can't remember what it's called. But it's like you're taking this model and you're saying the model's here, it's one thing here, and then later it's different. And you're somehow saying it's different, and somehow maybe the slope, let's say you were even thinking about a linear model. You're talking about the slope of the model up until 25 months, and then the slope of the model after 25 months. So you have to figure out a way to define a model that's general enough to allow to have 2 different slopes, one before 25 months and one after 25 months, And then if you want to see if there was an effect, you might compare whether the slopes changed. That's what you'd have to do. That's called an interrupted time series. I was involved in a study, paper published and stuff like that, and there's a data set. Somebody could work on that. You know, even though you can even have the paper, but I can give you a data set that you can work on that for your project. Interrupted time series. Okay, so these are a bunch of examples. More complicated, but I'm just saying this is what correlated data is. Okay, so now, let's see. I'm looking at the clock because got things to do, people to go, places to see. Okay, here's the next thing I'm going to do. After I do this, I'm going to skip. Oh, I got one other thing to do before I go to the next thing. Okay, this is the basic data layout for analyzing correlated data. So if you are going to address the homework question that's due next week, then I want to see if some volunteers may want to come up, and you can email me if you're willing to try it. You know, it's not the worst thing in the world. We're not out to cut you down. We want to, but anyhow, I want you to express yourself. In any case, this is the data layout. Okay, the data layout says there's a line of data that separates the clusters. This is the first cluster. Everybody in this cluster, it basically assumes we've got like cluster data on individuals. So this is subject 1. It could be a household. Could be household 1. This is subject 1, and there were n sub 1 observations in on subject 1. And this is subject K, the last cluster, the last of the clusters, and this is the n sub K observations, and they could be different. Okay, so what we're doing is, for each cluster, we're having as many rows of data as we have observations within a cluster. So the first cluster, we have n sub 1 rows. The last cluster, we have n sub k rows. And the ith cluster, we have n sub I rows, because we're allowing the number of observations within the cluster to be different. That's what the data layout looks like. Well, at least as far as subject and repeats. Well, what about the time? Okay. Well, it may turn out that the time is something you want to put in the model. You may actually want to have what's going on from in terms of the outcome, in terms of how time affects the outcome. So that may be that may be one of the X's. So you might want to have time. Time is listed over here. Now, if it turns out you're dealing with households, you don't have this column. You don't have a time column. Okay. But anyhow, I've got the times for cluster 1, cluster I, cluster K. And then I've got Y and the X's. Okay, Y is the outcome, and I'm allowing for n sub 1 values of the Y in the first cluster, n sub I values of the Y in the ith cluster. And then I've got the predictive variables. One of these might be the exposure variable, and the other variables might be variables that you want to control for, and some of these X's might even be product terms, exposure times variables you want to control for. So that's the general data layout that you're dealing with. Now, one thing we've already seen is that that's what the data layout generally looks like. Okay? So when you start thinking about your project and whether you have a legitimate project to work in this course, you've got to think about what the data layout is, whether it fits this data layout. Now, one thing to notice is that if it turns out, when you look at the Y, the outcome variable, okay, if it turns out for every subject in the study, Y doesn't change, all these Y's are exactly the same value, you don't have a correlated data study, right? Because the key thing is you're allowing the Y, the value of Y, to change at different times or within different clusters. So that's, you got to have that. Okay, you got to allow for the Y to change. Okay, now what the X's are, X's could be time independent, time dependent. They could be you could have X's that are confounders. They could be product terms, and so on. And how they're defined is up to you in terms of what you're trying to do with your study. So that's what the data layout looks like. Now, another key thing about this data layout is, does the data actually come this way? Does data actually come this way? If you have a study and you've got 100 subjects, K is 100 subjects. Do you have the data so that for each subject, the data, you have a different line of data for each subject? Often what happens is for each subject, you have a long bit of information for each subject. So you actually have, this is, in a way, you might call this a vertical layout, because this is listing what's happening per subject underneath one another, within a cluster, one underneath one. But typically the way the data often comes, not always, but the data often comes horizontally. So for each subject you have it that way. Okay. So if you have it that way, you need to get it this way. Okay. So there's often some data manipulation you have to do to get the data in this form. Okay. Now there is a program, and I put it on the it's in the lecture material notes. There's a program that my colleague and co-author Mitch Klein wrote that actually gives an example of how to go from horizontal to vertical for a very simple example. And you should find that, you know, because it'll help you deal with this problem. And I may mention it another time, in another class, not in this class. So if the data comes horizontally, you want to get it vertically, there's a way you can do that. I mean, there's the hard way, figure it out yourself, or the easier way is you look at Mitch's program. It's a program that you could use to modify for your situation. Okay? Okay, now, last thing I want to say, I'm not finished, but the last thing I want to say about this part is what are the alternatives to correlated data analysis? Okay? In other words, why are we doing this? What are the alternatives? Well, one alternative, and this is what people used to do before these programs were available, before GenMod and Mixed and everything, before they were written. They basically said, let's just assume everything's independent. Let's just assume it. Let's just treat it like, you know, even though we got repeated measures, let's forget about it and run so they're, you know. So that's one alternative. Another alternative is you've got within a cluster, within a household, within a person, you got several observations. Just use one of them. Don't use all of them. Okay? That's another alternative. And a third alternative is, well, not just use one of them, come up with some kind of a score, a summary score, an average. You got blood pressure measurements on 6 times, get the average of the 6 times, so use one. Okay? Those are all three you know, options. And they all have their pros and cons. I mean, the advantage of one is that you don't have to go through all this mess. Okay? The disadvantage is you may get the wrong answer. That's bad. You may get incorrect inferences if you just assume everything's independent. And I have some examples. That Cannon paper that I'm asking you to read is an example to show that you can get incorrect answers. Now, the other two situations, the other two alternatives, they make sense because it helps you to simplify the problem in the sense you don't have to deal with this multiple set of observations within a cluster. However, what you're not doing is you're not using all the information, you're summarizing it. So you're not getting the nuances between different observations on different subjects, on different observations within a cluster, on the same subject within a cluster. So alternatives 2 and 3, you know, do not use all the information. So that's why we have this course, because these things that people may have tried to do aren't necessarily the best things to do, but they're things that people do. And particularly number 1 is really dangerous. Although number 1 may turn out to give you the right answer, that when you try to do all the complicated things you do to deal with the correlation structure, you wind up getting no different answer than what you would get if you assumed everything was independent. But unless you do it, unless you try it, you don't know this. Okay, so okay, so I'm going to stop with that, but I'm not stopping because I want to go on to something else. Okay, we'll talk about random effects. Okay, what a random effect is. Okay, and how it differs from a fixed effect. But I particularly want to talk about a random effect. Have you had something about that somewhere in your courses up to this point? What a random effect is? And where? If you had it, where did you have it? Bob Lyle's course? Did he talk about random effects? in the EPI 5, BIOS 591? I'm looking, nobody's moving. You're stone, you look like stone. Okay. So I don't know, maybe you've never, so let's talk about what we mean by a random effect. Okay, and there's a number of different ways to do it. Okay, but now the reason why you need to talk about this is that when you're using not any of these programs, we're using proc mixed, which is what we're going to focus on mostly. When you're using proc mixed to deal with a continuous outcome, you can have random effects in your model or just fixed effects. You can have just fixed effects, you can have random effects, or you can have both, fixed and random effects. And you have to make a choice about whether you want to use just fixed effects or random effects or both in the model. You have to make a choice. In order to make a choice, you have to know what you're talking about, right? So we have to talk about it, okay? So, and that's true for Glim Mix too. For Glim Mix, you can choose it. You can choose it. Now, GenMod only lets you do fixed effects, so you can't even have a choice there. So that's a problem with GenMod. But let's talk about what a random effect is. A random variable that is included in a regression model to account for the effect of the natural heterogeneity among subjects on the prediction of a response variable of interest. So the key thing is the natural heterogeneity amongst, what does that mean? Okay, let's see what that means. I've just written two models, okay? And both these models are linear models, right? They're both linear models. The outcome's y, not the p of y equal to 1 or not a logit or anything like that. So it's y, okay? Now you notice in the first model, that's the outcome variable, y, the jth outcome on the ith subject, okay? And then there's xij, that's the predictor. That's the x value, the predictor that you're interested in. I'm just assuming now that there's only one predictor of interest, your exposure, say. Okay? And then this part of the model has a beta naught, an intercept, and a beta 1, a coefficient of the x variable. Okay? And beta naught and beta 1 are called fixed effects. Okay? Now, in addition to this part of the model, there's two other parts of the model. The thing on the far right is the E term. What's the E term stand for? The error term. What's left over after you use whatever else you want to use to predict y. Part of which is this, but another part of which is this. B0I. Okay, now you notice that beta 0 and beta 1 are Greek letters, and E and B are not Greek letters. What are they? Latin letters? That's what some people say Latin letters. I don't know whether it's Latin. American letters. No, I'm going to say that. Okay, in any case, they're Latin letters. Okay. Now I'm just looking at this model. Okay. Now you notice the B0I is the B and the E represent values that are changing for the ith subject. B0I will be different depending upon whether you're talking about the first or the second or the third I subject. Beta 0 and beta 1 don't change. So this is something that changes with the subject. So this B0I represents how subjects, individual subjects, are affecting what happens to y. That's what I mean by the natural heterogeneity among subjects. Because if we're talking about I equal to 1 or I equal to 2, this could be a different value. And this could make a difference in what y is, depending on what we're talking about. So that's what we mean by that. And the EIJ is the error term that you get once you consider what the x does, and you consider what this does, this is what's left over. Okay. Now, why do you want to consider something like this? I'm not going to even look at the second one. Why do you want to consider something like this? Well, think about this. When you're doing your study, suppose it's like a clinical trial, so you don't even worry about controlling. You may be aware that when people do clinical trials, they often don't want to even control for any other variables because they assume they're balanced out in the trial, which may or may not be the case. But suppose it's like a trial, and the only variable you're interested in is this X variable, the exposure variable, okay? So you don't have any other variables you want to control for, okay? So you want to predict X from, you don't have any other variables that might be different that you might want to, that you haven't even identified that you might want to control for, okay? But it turns out that, it may turn out that this exposure variable is not the only variable that affects the outcome. And you don't know what variables affect the outcome. You've decided that variables that you might think about, they're not going to change, or hopefully they're balanced, but there may be some that aren't balanced. Okay? And so what this is supposed to reflect, B0I, is any other combined result of what other variables that you haven't taken into account is going to do in the help in the prediction of the outcome. So it represents the contributions of different subjects to the outcome without trying to specify a particular variable that you don't know what to specify. So that's what this is. Okay? It represents what the ith subject does to predict the outcome over and above what the exposure variable does. Now, let's look at the second one. What's the second model? Second model is also a linear model. Okay, what's going on here? How's the second one different? Second one has a beta naught and a beta 1, but now it has two B's in there. It has a B0I and a B1I. Okay? Now the B0I, if you think about it, you notice the B0I over here, without even considering it over here, is sort of like beta 0. Beta 0 is the intercept, okay? And B0I is sort of an extra little extra effect of the intercept. It's an extra something that has to do with the ith subject. It's how the ith subject might affect the intercept, or how the intercept may change for the ith subject, okay? So what does B1I do? What does this one do? This basically says, well, not only might the intercept sort of have an effect on the ISO, but it may turn out the slope of the variable that you're trying to predict also has an effect. So if that's the case, you're allowing for two random effects, a random intercept and a random slope. So these are two examples. Now you can have a logistic model with random intercepts and random slope, but that's what you mean by a random effect. Now to see this even a little bit better, let's just look at this picture. This comes from my friend Mitch, my co-author Mitch. Harry, Barry, and Gary. Okay, you'll remember this because of Harry, Barry, and Gary. This is Mitch's favorite team. Harry, Barry, and Gary. Okay, you're trying to consider a study that relates to the age to systolic blood pressure. And you got a whole bunch of people in the study. Harry, Barry, and Harry, Barry, and Gary are three of them. Okay, and on each of the people in the study, you've measured the outcome variable, systolic blood pressure, several times. On each person. On Harry, on Barry, and then everybody else. You've measured more than one time. So you've got repeated measures on the outcome. I'm assuming you have that. Okay. Now, you see this black line over here, this black line. It's a linear regression line that relates age to blood pressure for everybody, for all the data together. Okay? In other words, if you just ignore any individual person and you just do a linear regression of y on x and you don't consider any problem with lack of independence or something like that, and you just lump everything together and you do a linear regression, proc reg, this is what you get. Okay? Now, what is this doing? These are the linear models for three of the many people in the study, Harry, Barry, and Gary. What's the difference between Harry, Barry, and Gary and this summary thing? Well, what happens is Harry, Barry, and Gary have their own intercept. They have their own contribution to the intercept. There's some natural, if you don't account for this random intercept problem, you're missing something. because Harry, Barry, and Gary have their own contribution to the intercept. Okay, so that's the reason why you want to consider a random intercept in this case. In fact, just to make it a little bit clearer, if we just look at Harry, for example, we may have 4 observations at 4 different ages on Harry, and we plot them, okay? And Harry's line represents the line that goes through Harry's observations, and the intercept for Harry is different than the intercept for the average one, okay? So that's what I'm saying. What I'm saying here is Harry has its own contribution, his own contribution to the intercept, and that's why we might want to consider putting in the model a random intercept to reflect the fact that different people contribute their own make their own special contribution to the overall effect. Okay. Now let's look at the next picture. You'll remember this, because this is Holly, Dolly, and Molly, as opposed to Harry, Barry, and Gary. Okay. So what do we see about Holly, Dolly, and Molly? Well, first of all, you see the black line over here. Again, it's age on blood pressure. We're assuming we've got, these are women, we assume we've got several observations at different ages on each woman, and this is the summary relationship between age and blood pressure, and that's the intercept for the summary thing. Okay. So what's going on with Holly, Dolly, and Molly? What's going on with them? Not only do they have different intercepts, but they have different slopes, right? Holly has a different intercept and slope than Dolly, than Molly, okay? So this is a situation where it may turn out that not only are the individuals make a contribution to the intercept, but they make a different contribution to the slope, okay? And if you look at it in terms of, for example, Dolly, you might have 4 measurements on Dolly, and Dolly's line doesn't look the same as the average line because Dolly contributes something specific to the intercept and to the slope. Okay? So if you have this particular situation, then you're talking about wanting to consider having a random intercept and or a random slope in the model to reflect the fact that these individuals in your study make a contribution to the outcome over and above whatever the predictive variables you're using in the model. That's what you're doing. You're saying they represent some extra thing over and above what the individual variables, the individual predictive variables in the model, and that's you reflecting them in here. But these are variables, they're not parameters, and so they have to be sort of treated somewhat differently when you're running the model. They have different characteristics. If you talk about the variance in here, the fact that the model, for example, this model, you talk about the variance of y. The variance of y depends upon not only the variance of e, but the variance of these 2 b's, because these are random variables. And it gets a little bit more complicated to work out what the formula looks like. We're not going to worry about that right now. But the main point here is that's what a random effect is. A random effect is a variable, it's a random variable, not a fixed variable, not a parameter, a random variable that's included in the regression model to account for something over and above what the predictors in the model you're using, something over and above what the predictors you're trying to work with. Now, there's even a second way to talk about this, and I'm just going to be brief about the second way to talk about a random effect. A random effect is a coefficient in a regression model that corresponds to a random factor. A random factor is a variable in a regression model whose levels are regarded as a sample from some large populations of levels. This is a different way of talking about what a random effect is. You might have heard it this way when somebody first talked about analysis of variance somewhere. So what I'm saying here is if the variable of interest is drugs, the variable, your exposure variable is drugs, say, and the specific drugs being studied are considered to be a sample from a larger collection of drugs of interest. So let's say you're doing a study, and the study involves 3 drugs, okay? And you want to consider a model that has the variable drugs in the model, a variable that reflects it as 3 drugs. What would you usually do? What would you do if you are only interested in those 3 drugs? How would you put that in the model? How would you put the drug variable in the model if you had a variable that had 3 categories? What would you do? You remember? 2 dummy variables for the 3 drugs, right? Okay. if you're only interested in the 3 drugs. Okay? However, suppose those 3 drugs were not the only ones you were interested in. Those 3 drugs represented a sample of drugs from a larger collection of drugs. Then you don't want to put in 2 dummy variables for the 3 drugs because that's not what you want to do. You're going to actually consider drugs as a random effect. That's what a random effect is. Okay? If you're only interested in drugs, the particular 3 drugs, then drugs is actually considered as a fixed effect. As a fixed factor. And the coefficient of the drug variable is going to be a fixed effect. But if you're interested in drugs as something that's, you're not interested in the specific ones, you consider a larger collection of drugs, then you're talking about drugs being treated as a random effect in the model. And drugs is a random factor, and the effect of drugs is a random effect. I'm not really saying it as good as I would like to. But anyhow, that's what you need. Now, this is a start on this issue about random versus whether you're dealing with random effects or not. And one of the things you're going to have to decide in this course is when you do your project and when we do any analysis, whether it's linear or nonlinear model, we have to decide whether we need to have random effects in the model or not. And in order to do that, it's not that easy. And I'm just trying to at least start on how you might do that. And later, I actually have, this is the end of, this is the last slide in this thing. I'm not going to go over it, but the last slide gives you a guideline about when to use random effects. But I'm going to put that off until we actually get to it. Until we get to it in the context of some examples. So anyhow, wanted you to know a little bit of the difference between, we're just introducing it if you haven't ever heard of these things before. Okay, now, got one more thing to do. One more thing to do. Okay. And I may not finish it, I'm going to start it. One more thing to do. This. And this is actually not that hard to understand, but at some point, I'm going to, let's see, where's the hourglass? I can't see it. There it is. Okay. This is the Demi-Danko example. I don't know who Demi-Danko was. He's related to Putin. No, I don't know. Demi-Danko. No, he's not. Okay. Okay. This is a business study, business data. Okay. And so what you've got is you've got these commodities people are trying to sell. Okay. And you've got 19 commodities. 19 commodities. 19. I don't know, hairbrushes, I don't know, 19 things you're trying to sell, okay? Different types of hairdressers, okay? And what you know is that these let's see, N sub I is the number of sales by price. Each one of these commodities has been offered for sale maybe more than once at different prices. And then, in other words, the X is the price of the commodity at any one of a number of times when the commodity was offered for sale, and Y represents the number of sales you actually got when you offered it at a certain price. So this is a scatter plot of price on sales. And what the idea is there a relationship between the price of the product and how much it sells? How often it sells, or how many sales you get. Okay. Now you notice I've drawn this picture. I've drawn this regression line. Does that make sense? I mean, look at the line. Does it make sense given the plot? It makes sense. Okay. Now, one reason why it doesn't make sense is that it doesn't consider that some commodities have been offered for sale more than once. So it doesn't consider the fact that if commodities have been offered for sale more than once, that the different sales on a given commodity are correlated with one another. And this is ignoring that. This is just treating all the data as independent. That's what this has done. I don't know if you follow me. I know it's late in the day here, so I'm going to go back to this thing, but I want to introduce it right here. Okay. Now, look at this picture. What have I done here? Well, what I've done is I've got the same. What I've got here is all these circles here, but what I've done on this slide is you see these two dots here correspond to the same commodity, the first commodity. And these two dots correspond to the second commodity. And then there's all the other commodities, the 12th commodity, the 13th, 14th. Now, what do you notice if you draw the lines to connect the commodities, and you look at the commodities, what's the relationship between price and sales? It's positive. It's not negative. Okay? That's what I'm trying to tell you. Positive and not negative. So if you ignore the fact that if you treat this as independent, you're going to get like there's a negative relationship. And if you consider what's actually going on, you get a positive relationship. Okay? So how would you do this? How would you do this if you're doing the analysis? Well, the first thing you do is you'd say, okay, let's look at the data. Well, I put the data out here unordered by commodity, but then on the next slide, I've got it by commodity. You see, subject 1.1, that's the first commodity. Subject 2.2, that's the second commodity. That relates to the first commodity had two prices, and the second one had two prices. And some of these other commodities have more. But anyhow, that's the data set. Now you notice, what's the form this is in, the data layout. This is the form that I talked about, the data layout for analyzing correlated data, isn't it? Because I've got cluster 1, cluster 2, cluster 3. How many clusters are there? There are 19 clusters. Okay, that's what I'm saying. There are 19 clusters. So if I now consider the fact that there are clusters, and I want to consider the fact that there might be correlation, well, look at this model. Look at this computer code up here. This is the last two things I'm going to do before we quit here. I'm going to quit by 20 up. Look at this code. What does this say? It says proc-reg. What does proc-reg mean? Linear regression, right? Linear regression. And then it says data 1. That's the name of the data set. Model sales equal price, so the outcome variable is the sales, how much was sold, and the price is whatever the price was. And then it says plot sales by price. Give me a plot. And when I run this thing, what do I get? What's the coefficient of the price variable? That's the predictive variable. What is it? It's negative. What does that say? That says there's a negative relationship between price and sales. Okay. What have I done here? Independence or non-independence? I've assumed independent. I haven't done anything about correlated data. I've just run proc-reg. Everything's independent. See that? Okay. Now look at the next thing. Oh, that's the plot. That's the same plot. That's what happens when I plot it. It's the same plot as I showed you before. Okay, look at this next one. Now I say proc-reg data equal 2. It's actually the same data set. But what have I done here? Sales is the outcome. Price is one of several independent variables. What are the others? S1, S2 up to S18, what are they? There are 18 dummy variables for 19 commodities. That's one way I could consider the fact that I want to control for the fact that the commodity has an effect here. I want to consider the effect. I want to control for commodity in some way. This is not technically correlated data, but I'm sort of doing something like it. Now, when I run this, notice the coefficient of the price variable. What is it? Positive. So that's a better way to do this. Okay? Now, I'll show you one other way, and then we're going to stop, and we'll look at this thing again. Look at the next, and this is something that we have to get familiar with later on, but look at the next set of code here on the top. Next set of code at the top. It says proc mixed. I'm not using proc-reg, I'm using proc-mix, which we haven't talked about how it runs and all that, so I'm just giving you a little code. Data equal to 2, same thing. Class subject, something I put in here, why, we'll have to talk about. Model sales price, so I'm just using sales price, and then I have /s, now the S tells the computer to give me the solution, give me the regression solution. And then I say random intercept. What do you think I'm doing here? Random intercept. What am I doing? Remember I was talking about random effects? What am I saying is a random effect here? Okay, I have 19 commodities. What's the random effect? The commodity. In other words, the commodity has its own specific influence on this thing. So I'm putting in a random effect, and the way I do it in proxemics is random intercept. Okay, and then I have to say something in order to get it right. But that's the you see the model over here. I'm now in the sun, so I can't. You see the model over here in the box. See the model that I've written? Have you seen that model before? It's the same model that I showed you before. Now it's related to the sales and the commodities thing. Now look at the outcome, the edited output. What I get. The effect, intercept, and price. When I run this thing, what do I get? Is it positive? The coefficient of the price variable positive or negative? Positive. What does that say? There's a positive effect of price on sales. Is it the same as what I got previously? What did I get previously for the coefficient? 46? What do I get here? 41. I don't get the same thing. Why don't I get the same thing? Because I'm not doing exactly the same thing. I'm doing it sort of similar, but I can do this using proc mixed by actually taking into account the correlation structure in a way that allows me to do it in a way that's different than forcing me to say that I'm only interested. See, this says I'm only interested in those 19 commodities. Remember how I talked about if you're only interested in the 19, then you're going to do it that way. But if you want to consider the 19 commodities a sample from a bunch of commodities, that's the way you want to do it. And what you get is essentially the same conclusion. Okay? So this is just an example of what happens when you do correlated data. And this is an example of using a random effect, in this case a random intercept, because you're saying commodities are different. They have their own, you have to take into account the commodities. Okay, so we're done. So next time what you're going to do, we're going to talk about matrices. I'm going to maybe review this a little bit. I'll give you a review of everything we've done. And then I want you to look at those homework things. I want you to look at the matrix thing, and I want you to have some volunteers talking about a project or an example. Thank you. Five minutes early. Wow. Great. Yeah. Okay, let me just do something. Stop this.